Okay. Today, so I want to look at with you guys. I know it's going forward a bit, but like in the 52, 54, and well, I want to talk about how do you incorporate energy to solve a question like this, where it's a block and a slide down, and then fly off a surface like a projectile. This might also look familiar to you, the one where you're going over a ramp. And then this 57, like a loop-de-loop type question. This has a fascinating answer to it. Does this look familiar to you? Remember we talked about Stuntman Bob, how fast is the question we asked was how fast does Stuntman Bob have to be going at the top of the loop in order to sustain his circular path? Well, we're gonna ask, assuming it's just, well, it's actually not a person in a car this time, it's just a frictionless block. How fast does the block have to be moving down there in order to be able to make it around? So that's a slightly different question. Does that make sense? Okay, so let's get into it here. 52 says a 5 kilogram block is initially at rest at the top of a frictionless ramp on a platform. The platform is 10 meters tall, and the ramp is 8 meters tall. So let's label the diagram. This is 10 meters. I didn't really draw it to scale. Sorry. Close enough for government purpose. And then it's kind of what you think is going to happen is going to happen. It's going to slide down the ramp, and then it's going to fly off the ramp and land over here. Everyone okay with that? So here's a question for you. Which is the easier question to answer? There's two questions. One says, how far will it land from the base of the platform? And the other question asks, how fast will it be going just before it hits the ground? Which one of those questions do you think is easier?
Velocity.
Velocity is actually extremely easy. This one's not easy. So let's, should we just do this one first then?
Yeah.
Watch how easy this is. This is the beauty of energy. This is a complicated path, right? Because this could be like, this could be like a circular path followed by a parabolic path. You know, you could do some crazy vector calculus on that, but we like to use energy. So we say, how much total energy is in the system here? What's his total height? 18. So it's going to be mgh. So I'm calling the ground a height of 0 meters. So the ground is 0. This is 10. This is 18. So mgh. Does he start off with any speed? It says initially at rest. So can someone quackulate that for us? 882 joules. Okay, so we feel okay about that? Fun fact, imagine being hit in the face by that. 18 meters is pretty tall. Now there's a point here. A 5 kilogram block, that's like over 10 pounds, okay? Slides down an 8 meter ramp, then flies off a 10 meter ramp, platform and hits you in the face. That hurt a lot. That's how much energy your microwave puts out in like half a second. It's kind of amazing.
That video where someone brings their microwave to turn on without the door.
What?
I saw a video where someone it was on TikTok, and someone made a thing that they put on their microwave so they could use it without the door on.
They wanted to heat up what?
Well,
They wanted to run the microwave with the door open.
well, they do edit like a Hey Green video that said don't Run your microwave with the door open, because it's bad.
Uh-huh.
You did it.
Oh.
Video of the little kid putting his cat in the microwave.
Oh my God.
His cat in the microwave.
No.
He's like live streaming and he puts the cat in the microwave and he's like, how long can I put my cat in here for? And it was really funny.
That's gotta be fake, right?
No, he was actually doing it. And then the cat was like, don't do it. He's like, oh, okay. He takes his cat out.
Oh my
It was
goodness.
really
Jeez.
funny.
Okay.
That should be the answer.
God, I hate everything. Okay. So this thing's got 882 joules of energy. So when he reaches the bottom, all that was all potential energy up here. By the time it hits this, there's no more potential energy, right? Because the height is 0. So all that's been converted to kinetic energy. So the answer to this question would just be 1/2 m times v final squared has to equal 882 joules. Everyone understand that? So solve that. Should be relatively straightforward. And then you go, hopefully, if you reflect on that process, you go, wow, that's like, despite how complicated the path is, it's an extremely easy question. Because energy allows us to basically just look at the height. We don't have to look at the steepness of the ramp. We don't have to look at time. That's another good one, right? We don't have to know how far he traveled horizontally, for example. None of that's relevant to an energy calculation. All that matters is how high up are you and how fast should you go. Okay, what's the answer?
18.8.
Okay, sweet. Thanks. Now, this one's a little bit harder. You guys maybe recall doing those questions where we would calculate, if you knew how fast the thing was going at the top of the ramp, you could calculate how fast or how far it was going to fall. I phrased that stupidly. How far from the ramp it would land, the horizontal displacement. So that means we have to figure out how fast was the block going right here. Is that an easy thing to do? Yes. Just do the exact same process, except all you got to do is go, well, here, what's my energy calculation? I've got m g
times 10.
his h is 10, so he's actually got potential and kinetic energy, right? So at this moment, he's got potential and kinetic, and of course that has to equal 882. So let's solve that. What do we get there?
One side's 490, so that's gonna be 3.522.
What'd you get?
4.522.
So it's pretty small.
Do you agree with that, or
Yeah.
Julie agrees? Okay. Makes sense to me. So now, to figure out the displacement, what kind of quantity do we have to get involved? That we haven't got involved with actually for a little while now. Time, right? Because I'm gonna have to figure out what the process is. Here's the thing about learning physics, is it's not so much about knowing the formulas, it's more about just knowing the idea of like, if you understand things, you can go, well, I have to know how much time it's gonna take for this thing to fall. And then I can just use that time value I find to calculate how far it would travel during that time. And then once you know that, you can like look up a formula, right? You can like, does that make sense? It's not about memorizing the formulas, it's about just understanding what kind of quantities should I look for in this scenario. So anyway, I gotta ask the question, how long does it take something to drop 10 meters? So the formula for that would be, if I say I looked that up, it's gonna end up being basically, you guys might remember this. Remember that one?
Yes.
This would be the relationship between the height of the building and how long it takes for the object to fall. And since the thing is traveling horizontally, there might also be a plus V naught T here if the thing was like going up or down initially, but it's not, it's going horizontally. So anyway, the height is 10. G is 9.8, of course. And so you're going to get something that's roughly the square root of 2. I think.
Is Julia Sonderline here?
It was like 1.4. Let's get one more decimal.
3.
Okay.
That's rounded.
Not meters per second. What am I doing? Silly. What do I do with that? Are we almost done? Is that like, are we like pretty close to finish with the question, or are we still kind of have a lot of steps to do?
Well, you gotta find the distance, you gotta.
It should just be one more equation, right?
Well, yeah, I mean, but remember, and you got it? I thought I heard you say it in the answer. Maybe I was just hallucinating. That's possible. We know the velocity, right? We know how fast he's traveling horizontally. Right there. And we know how long that's going to take place for, right? Because we know how long it's going to be being a projectile for. So what's all I got to do? Multiply that. The horizontal displacement is just going to be that velocity, 12 meters per second, 12 and a half meters per second, multiplied by the time, 1.43. And that's going to be our answer. What is so that's like 18 or something?
It's 17.9.
Thanks. All right. So that is how far it would have traveled horizontally before it hits the ground. Cool beanies? Do we feel good about that? Maybe? Do we feel sad about it? I don't know. So when you do 50, or not when you do, sorry, 50, I'm all out of whack here. Is it 54? Using all those symbols, it's gonna come out. You know, the same exact process will bear out. So you're gonna have, you know, this will be mg. By the way, what quantity do you think is gonna drop out of all of the equations? The mass, yeah. So the 5 didn't really matter. It's nice to have a number because you can just get actual like concrete values for your energy and stuff. But
If you don't have a number, can you make one up?
you could, yeah. But for that question, 54, or no, it's 53. Who said 54? Was it just me? 53. For 53, yeah, you're going to use m, but you're going to see the m just get cancellated into the very first steps.
Oh.
So you're going to see h sub p, h sub r show up in your final answer. You're going to have g show up in your answer. Okay, so I want to do the Humpty Dumpty problem. 54. I devoted a whole page to it. Humpty Dumpty. He sat on a wall. Okay. Okay, so this guy's a 10 kilogram block. He's traveling to the right at, we don't know, some initial velocity v. And the first question asks us, what's the minimum, oh, and it tells us the radius of this ramp. So the radius is 1.5 meters. So the question is, what's the minimum initial velocity here that would allow the block to make it over to the other side of the ramp? Okay. So how do you think energy is going to help us for a question like this?
Well, you just need to calculate how much energy it needs to take to go to the height of 1.5 meters.
Right, and then Bailey, what were you saying?
If you calculate the amount of potential energy you would have at the top, it would give you the minimum amount of kinetic energy you would need to get to that point.
Yes, exactly. Yeah, those are both exactly correct. So, okay, so yeah, you up here say imagine he got it. Now, if you're assuming he barely makes it over, then up here your velocity is going to be roughly 0, right? Maybe it's 0.01, but it's assuming he's going to go up and then barely make it over. So up here, exactly like you guys said, to calculate that potential energy. So the potential energy up there would be mg times h, which is, I think that's right. Someone confirm that. 15 times 9.8. Sounds right.
Yeah, that's right.
Because 10 times 1.5 is 15.
That's
So, okay, that means he'd have to have that many joules of energy to make it over, right? By the way, this idea here gets used in like nuclear physics and crazy, like, it's amazing how far this idea stretches in science. This idea of like, oh, like he needs a certain amount of energy to get over the hump. They talk about that when they're talking about like an electron being bound to bound electromagnetically to like a nucleus, and then like talk about like a nucleus, can it break apart or not? And anyway, so just want to throw that out there. So if you keep studying, if you go further in your education physics wise, this kind of idea comes up over and over again. Anyway, so let's do, assuming that he has that much energy, so 1/2 mv squared, set it equal to the energy we know he needs to have, and solve. Right? You're gonna get, I don't know, 5, something, 5-ish, maybe. Okay, let's just go 5.4. Okay. So if he had been going 5.4 meters per second, he would barely make it to the top, and then assuming he had just enough energy to get like an extra millimeter, this is called an unstable equilibrium, if you're wondering, you want some fancy lingo. Because if you're teeter-tottering at the very top, a tiny little bump either way can send you off the hump. Now B says, if the block's initial velocity were 6 meters per second, which is a little bit bigger than that, how much force would the track exert on the block at the moment, at that top moment? Okay. So for part B, what do you think is the first quantity we're going to calculate? That's the last quantity we're going to calculate, right? That's what we're trying to solve, right? So in order to calculate that, we need to figure out, well, how fast would he be going at the top if he had been going 6 meters per second down here? Does that make sense? Okay, then let's do that calculation. Assuming, so it's sort of a new setup, but I don't know if anyone is doing this to keep their thoughts straight, but I'm gonna write it down here. Okay, so for part B, his initial potential energy is what at the start? 0, and his initial kinetic is 1/2 times 10 times 6 squared. And at the top of the ramp, he's mgh plus 1/2 mv squared. Is everyone okay with this, the way I wrote that? Okay, so take Mr. Quackolator and calculate V. By the way, for clarification on energy questions, showing your work, like if you just have this line and then the V value right underneath, that's like very sufficient. As long as you're showing like how are you calculating, how are you setting up the problem, you're good to go. So let's see, 5 times 36 minus 147 divided by 5 is the square root. I'm getting, tell me if you agree, 2.57.
Yep.
It's a nice number. 2, 5, 7. Right, Taylor?
Yes.
These are nice numbers.
It's
Anyway,
a bad number.
it's a bad number too.
No, what is a bad number to you?
A bad number? I don't know. Not many.
7. because you-
2, 5, and 7. They're all prime. Just missing 3.
And 11.
Also, 2 plus 5 makes 7. Lamau?
Well, no.
That's a good Lamau right there. Okay. So the question asks, how much normal force is there? So the answer to that would be, again, you got to go into your memory maybe and say, oh, I know how to do this. Like we've done this problem where if you know how fast the thing is traveling at the top of the circular path, you can calculate the force. So at the top of the hump, little force diagram here. How much force pushes him down? Gravity, so he's
98.
98 newtons. So there's 98 newtons pushing him down. And there's some smaller amount of newtons pushing him up. This is called the normal force from the ramp. Right? And then if I write a really famous equation, F net equals MA, the net force is the 98 minus the normal force. And then, who remembers this one? What's the A?
V squared over T.
Close.
V squared over R.
V squared over R. So the mass is 10. Acceleration is V squared over R. It's called centripetal acceleration. Are y'all cool with this? Yes. So he's 10 kilograms mg. So 10 times 9.8.
It's seriously good.
Oh, Mr. Quackbillator. What is 98 minus 10 times 2.57 squared divided by 1.5? This is one of the nice things about these calculators. They're insanely overpriced, but doing stuff like this, that it becomes very easy.
Oh, yeah.
It's like the only good thing about it. Okay, I'm getting 53.97. Good question.
Newtons.
Units are a force would be newtons. Which is almost, it's a little bit more than half, right? His like usual weight. You gotta be like, hey, bro, how do you feel? How are your feelies? He'd say, oh, I feel a little bit more than half as heavy as I usually feel. Okay, it's good to know. Good to know. Okay, now this whole question is going to come full circle now. So hopefully it'll make sense. Now we're going to ask, because we already asked, what's the minimum speed does he have to just get over the hump? We've just calculated that. Well, let's say we bump up that speed, make it a little bit faster. We end up seeing that he ends up feeling lighter at the top of the hump. Now we could ask, part C says, what's the maximum speed he could have at the beginning without flying off the hump, right? You can imagine, if you're driven a car or gone skiing or snowboarding or skateboarding, yeah, if you go fast enough, you'll just fly off the hump. So yeah, the calculation would go, there's a trick to it, which is, exactly, yeah, very good. Because if you hit that critical speed, what if you were perfectly weightless at the top of the hump, but without flying off the hump? Then your normal force would be 0. So, so I'll be trying to box this in here. So maybe I'll do it over here. So for part C,
Exponential rate of 1
so for part C, if this is going to be the maximum possible speed that will allow him to stay on the ramp, then the normal force, the logic kind of goes in reverse now. You say, well, assuming the normal force is going to be 0, that means I can calculate the velocity at the top of the hump, right? With this idea. So if I write this same formula, but this time I go 98 minus 0 equals mass times v squared over r. Does that make sense, what I'm doing there? I'm basically saying how fast would he have to be going at the top of the ramp in order to be weightless? You sure that makes sense?
Yeah.
Okay. So let's solve that. So I'm going to go 98 divided by 10 times 1.5 and then take the square root. And I get about 3.83. We call it V top. That makes sense? So then you hopefully it makes sense how we're kind of like reverse engineering it. We're going backward. We're going to go, well, now assuming I was going that fast at the top, how fast would I have been going at the bottom in order to have that velocity at the top? So then I say, it's an energy calculation now. I say at the bottom, I had 1/2 mv squared. And at the top of the ramp, I had 1/2 mv squared plus mgh. Does that make sense? How we're going? Okay, so now let's solve this for the initial velocity. So I got to go 3.83. Well, I can just take the calculator's stored value, square it, times 5, add on 147, then divide by 5, square root. And you should get, cool beans? At this point, hopefully it's not, the math shouldn't be tripping you up, ideally. If you're getting tripped up by anything, it should be the physics. This is a very hard question. This is not an easy question. I just mean, are we all good with like, once you get to this step, it's pretty trivial just to like punch it in? So just, if you'll allow me, quick recap here. So we went, we said, if the velocity is 0 at the top, you can use energy to calculate how fast would you have to be going at the bottom to hit a 0 velocity at the top. Very simple calculation. Then we said, if I give you the initial velocity at the bottom, 6, so I say, suppose it's going this fast at the bottom, can you calculate, 1, how fast is it going at the top? Yeah, we can do that. And then can you use that velocity to tell you what's the normal force exerted on the object by the ramp? Okay, and then the last thing is, if I tell you that, well, if you're told indirectly that the normal force is 0 at the top, so if you know that by saying like, oh, it's gonna, maximum possible speed he can have without flying off. That means normal force is 0, and then you can use Newton's second law to calculate what the velocity would be, and then use an energy argument to go backward in time to figure out how fast would I have to be going to reach that velocity. So there's no questions? Feel good about it?
Like with the crack at home, and then I'll have
Okay, so.
Mr. Hall is also just kind of that amount of interesting relationship. Like